Okay, good morning, everyone. So we will start the remaining part of the Geology of Sri Lanka lecture. Uh, I think you can remember last time we discussed about the zircon overgrowth. That means metamorphism, right? So this is one image of a zircon grain. We use these zircons, as I mentioned in the previous lecture, in the mass spectrometer for the uranium lead system, right? For the uranium lead system, we use zircons for age determinations. Okay, right. So this is the isotopic system which has been applied to many Sri Lankan rocks. There, the zircon is the main grain to apply this geochronology system. So as I said, there are several methods, but two of them are very popular in the recent past. One is single zircon evaporation, and the other one is zircon spot dating. Okay, so in the case of zircon evaporation, all the zircon grain is dissolved, right? All the zircon grain is dissolved, and then that solution is used for isotope determination. But in the case of zircon spot dating, we don't have to do any dissolution. We can use the grain itself. Directly the grain can be used for dating. So this method is the most commonly applied method globally, and also for Sri Lanka, this has been applied extensively, right? So in addition to zircon dating, as we discussed last time, there are other isotopic methods: rubidium strontium method, samarium neodymium method, lutetium hafnium methods. But of course, there are other two methods like here, rhenium osmium and lead. But these methods have not been applied for Sri Lankan geochronology. Okay, so for the time being, we have the application of zircon, rubidium strontium, samarium neodymium, and lutetium hafnium for our geochronology. Okay. In addition, some monazite dating has been done. Okay. You know, monazite grain, it's like zircon. That is also an accessory mineral, which is also can be used for this geochronological work, right? So this has also been applied to Sri Lankan rocks, but only one study is there. Okay, right. So when we consider the spot dating, okay, zircon spot dating, we use the zircon itself directly, right? So there is something called zircon mount, which is rounded mount, rounded disc-like thing, very small, like 1 inch diameter, and there many zircon grains will be pasted, okay, separated from the rocks. So these zircons later will be polished by a grinder, like we do for thin section preparation, the polishing. This will be polished until a half of its thickness is exposed, right? Originally the zircon grain is like this, right? So half of its thickness is exposed by polishing, right? So you don't see the upper part. The upper part has been removed by polishing. So that phase is used for dating purpose, because it's necessary to expose all this area effectively. So that's why it's polished half to its thickness. And then there will be a technique called cathodoluminescence technique, CL technique. Okay, this CL technique, for doing that, there is a detector attached to an SCM, right? There is an SCM. SCM, you know, we have an SCM at our department. So, but we don't have a CL detector in that SCM. Okay, so this CL detector equipped SCMs are there. So using them, we can we can insert this this mount, zircon mount, into the SCM, and then we can image all these zircon grains so that we can see the internal structures, right? So this is the internal structure which you can't see with even from a microscope. You cannot see. These are chemical contrasts. Okay, these are chemical and structural contrasts, so that it will appear only in cathodoluminescence images, right? CL images only, right? So once you have this image done, then the sample is ready for dating, right? So this dating is normally done by several methods. There are equipments called SIMS, right? Secondary ion mass spectrometer, uh, or there are laser ion mass spectrometers, right? Laser ablation, we call laser ablation, LA, right? So these two machines can do uranium-lead isotopic systematics and give the isotopic compositions of these grains. So if we have kind of a zircon like this, these are very interesting because you have one some structures, different structures there. For example, here some core area, some different structure, and you have a rim area which has another structure. Okay, so normally what we do is a spot is uh, ablated, or spot is, I mean, it is bombarded with an ion beam, right? This type of a spot is bombarded with an ion beam, so you can see the mark of this bombardment, right? It creates a small crater in the grain zircon. So remember, this is like 100 micrometer size, very, very small, 100 micrometer or above. Grains are very suitable for dating, right? So if the whole grain is 100 micrometer, right? This whole grain is 100 micrometer, then you can imagine how small this spot is. Okay, so this is like 10 or 20 10 20 micrometer, like very, very small spot. You cannot see it with even a microscope. Only using a electron microscope you can see that, right? SEM, secondary electron microscope. Okay, so these different areas will be dated, and in our many of our rocks, very old ages have been given from the core area, right? Like 2 gigaannums, like 2000 million years, whereas the rim areas give some uh, younger ages, right? It's more or less like 550 million years, 550 MA ages are given from the rim area. So this indicates originally this grain was there, and there has been later overgrowth. Okay, so this is the original grain. Most probably, this may mark the original grain, right? So this light area, bright area, sorry. Okay, so this is the original grain. We call it a detrital grain. Okay, because there is a core region. So this is an old grain, very old grain. But later on, due to metamorphism, it has generated the new zone, right? This is the metamorphic area, metamorphic growth, right? We call it overgrowth, right? Because it is growing over the existing grain, right? So these are very characteristic for metamorphic rocks. You can see earlier grains, ancient grains are uh, overprinted by these metamorphic overgrowths, right? Sometimes you can see only zircon grains with this type of area, right? With this type of area, that means it's totally metamorphic grain. That means the entire grain has been formed during the metamorphism. So if you date, it will give you the similar age, like around 550 mm. Okay, in this case only the rim has been grown during the metamorphism. So in many of Sri Lankan metamorphic rocks, you can see this feature. We have both of these type of grains, older grains as well as metamorphic grains. Okay, so these are called detrital grains, and these are metamorphic zircons. This is detrital zircon, and this is metamorphic zircon. So This is how the zircon has been used for geochronology, because this is a very, very effective and very reliable dating method. People like this method because it has a very less uncertainty or error, okay, compared to other methods like rubidium, strontium, samarium, neodymium, or other methods, right? So zircon is very, very reliable because it is directly derived from magma. The grain is derived from magma, or it is derived from metamorphic process. So therefore you can directly date the magmatic event or the metamorphic event, right, using those corresponding grains. So this method has applied for in a mass spectrometer. So the laser ablation, the laser or SIMS, secondary ion mass spectrometry, ablated point. That means we told that there is a small spot created by that machine, right? So the material which were inside this spot is taken up into the mass spectrometer, right, inside. So it is like then it forms into a gaseous form, but it's taken up by the ablation technique in a tube, like very tiny tube, carries this material into the mass spectrometer, and then it forms into gaseous state, and that is accelerated into a magnetic field. And since it contains a lot of isotopes here, right, there are many isotopes. Isotopes means, they have different masses, right? The different masses of same element, right? So depending on the mass, they will be separating out, right? The higher goes there, the lighter goes this way, right? So like this separation is happening in a mass spectrometer. So with a computer, it can gives out the ion counts, how many ions were there, how many isotopes were there, and then the computer attached to this machine calculates its ratios and gives out the isotopic values in the program, right? So with those isotopic values, we can calculate the age of that particular zircon grain. So this is how it is done. And this mass spectrometry is a kind of a technique which is used like weighing of atoms, right? So the mass is very important. Mass separation is happening inside the mass spectrometry, right? There are several detectors, right, to collect these ions, different masses of isotopes, right? And then this is connected to a electronic system and a computer, and it gives out the result to the end user. Okay, so this is basically the most popular technique. So like this, the ages have been determined. So as I said before, two methods have applied in Sri Lanka. One is the single zircon evaporation and zircon spot dating method. The spot dating method that I just explained. In the single zircon evaporation case, as I said, the entire grain is dissolved, right? Entire grain is dissolved, and that solution is taken up by, again, a mass spectrometer. That solution is taken up by the mass spectrometer and gives us the same result. But in this case, it's a little bit difficult for dissolution, because zircon is a very resistant mineral. So it is, I mean, even for very concentrated acids like hydrofluoric or perchloric acids, it can't dissolve completely, right? It's very hard because of its robustness. So therefore, in evaporation method, you might not get proper results. I mean, complete results because of this partial dissolution. So it's an disadvantage in that method. But anyway, that is also put into a mass spectrometer, and in that case, actually, it mostly used mass spectrometer is there is something called TIMS, thermal ionization mass spectrometry. TIMS, okay, thermal ionization. In that case, the heat is the matter. Actually, this solution you can put here in this case and resolve into masses. But there is another way which has been using mostly in zircon evaporation. This solution, the solution, instead of sending into this type of mass spectrometer, it can be sent to TIMS where you have a filament. Okay, in the filament, on top of this, the drops of this solution is put. Okay, the drops of solution is put on top of the filament, and this filament then evaporate the material like here, right? It evaporate and put into a gaseous form, and then that gas goes into the magnetic field and dissolve uh, into the isotopes. Okay, so this is a very convenient method, but only difficulty is the dissolution of the grain. That is the problem. So sometimes you might not get proper results because of partial dissolution. So in that case, there may be some problems. So therefore, in most of the cases, people don't use this method in the recent history because of these disadvantages. So therefore, people prefer to use these spot dating techniques, spot dating methods, right? So both techniques have been applied to Sri Lankan rocks, and for single zircon evaporation method, there are some publications given with the zircon grains, right? So all these are coming from zircon grains. Long euhedral zircon grains of Sri Lankan rocks have given, these numbers are not important for you, okay? But just keep in mind that the temperature of evaporation is like this on the filament, on top of the filament. It's mostly like rhenium, rhenium or tungsten filaments are used there, right? Because they can bear high temperatures. And the ratios are, you can get some ratios like these, but you don't need to highlight these ratios. What you need is the age. Okay, so the ages have been given like 1.7 giga-nms, like 1700 million years or something, right? So irrespective of the morphology of the grain, more or less similar ages, very closely related ages have been obtained from Sri Lankan zircon. So that indicates these detrital grains, these old grains have deposited in, they have originated from this type of old age. So that is the implication for the rocks. But you as you understand, these zircon grains are incorporated into rocks, right? They are incorporated into rocks like sediments or something. So that means it's not actually by that time the zircon grain is already there, right? Because it is not the exact timing of the formation of the rock. This age corresponds to the timing of the formation of the zircon. Okay, uh, but we are uncertain at what age this zircon was incorporated into this particular rock. So that is a problem in dating techniques in most of the cases. But at least we know that our protoliths, that means the components that contributed to make this rock, was as old as like 1.7 lakh, right? That means the age of the zircon, right? So this is the protolith ages. We call therefore these as the protolith ages of the rock. But in igneous rocks, it's very easy because igneous rocks, the zircon crystallizes from magma directly. Okay, so the formation of the rock means, the formation of the zircon means formation of the rock in the case of igneous rocks. But in sedimentary rocks, that is not the case. Okay, in sedimentary rocks, what you get is mostly the provenance age. That means the age of the precursor materials. But in the igneous rock, by zircon, you can directly get the crystallization age of the rock. That means the crystallization age of the zircon itself, both equal. So remember, for meta-igneous rocks, we can directly get the age of the rock, but for sedimentary rocks, meta-sedimentary rocks, it's a little bit hard to get the exact date of their deposition, right? So this is a problem we have already. So our old zircons having like this age, 1.7 age, doesn't mean that our sedimentary rock was formed at that age. Okay, remember that can be even later formed sedimentary meta-sedimentary rock. Okay, but the thing is, its precursor material or its protolith, its parent materials have ages like this age. So this is also an important point. And some you can see here some ages have been derived from some rocks using the depositional age. Then for example, you can get a minimum age and maximum age, right? For the material for the zircon population that you have in the rock, you will get different ages because they are coming from different sources formed at different ages. So therefore, in a sedimentary rock, in a meta-sedimentary rock, you get various ages. Okay, you get various ages, including the metamorphic age. So the metamorphic age may be the youngest age, but the other ages that you get is more older ages, which corresponds to the precursor material ages. But at least you can get some time frame by getting the minimum age and the maximum age, uh, just to say that okay, the deposition may have completed by this age, because if you have a detrital grain with very young age, like say 1,000 million years, and from there onwards you don't have detrital grains but you have metamorphic grains, then you can say that okay, the metamorphic the deposition may have stopped by 1,000 ma age, at least close to 1,000 ma age, at least like that. Okay, so likewise, some age constraints have been determined for the three complexes of Sri Lanka. The highland complex, the minimum like the deposition age has been given as 2,000 million years, right? For the Vani complex, 1,100 million years, and for Vijayan complex, it's also the same, 1,100. But remember, for Vani and Vijayan complexes, these are mostly meta-igneous rocks. So therefore, it's the this is corresponds to crystallization age rather than depositional age. Okay, this should be crystallization age at 1,100 million years ago. And we have some granitoid rocks. Granitoid rocks means the granite, actually the granite rock, but later metamorphosed, right? Once the granite is metamorphosed, you can call it a granitoid, right? You can call it a metagranite also. Some people call it granitoid. Some people call metagranite. Whatever, it's all right. So the granitoid intrusive means the original granite rock which was intruded into the rock before metamorphism. That means some ages. For the highland complex, some granites gave ages in this range, 665 to 1,900 MA. So that means at very old ages, like 1,900 million years ago, we had some granitic intrusions into the highland complex. And also around 665 million years ago, there has been granitic intrusions into the highland complex. So this indicates at various times the highland complex was intruded by granitic magma. Okay, the highland complex is intruded by granitic magma, and after that everything was metamorphosed. So the granite became a granitoid at the metamorphic age. Later on, the metamorphic age, we know the regional grade granulite phase is metamorphism. Here you can see it's less than 665. It's like 540 to 610 actually. Although it's given like this, you can say it precisely 550 to 610 million years ago. Okay, 550 to 610 million years ago. Okay, so this is the metamorphic age. So you understand, at 665 the last granite was intruded, but after another like 100 million years later, that granite was metamorphosed, right? So this uh, was like granitoid. It became a granitoid. Right? For the Vani complex, also the same. Actually, even though it says 550 here in this table, you can consider it 550 to 610, even for the Vani complex, no problem. Right? The same age range has been discovered from the Vani complex rocks also. For the Vijayan complex, uh, it's actually amphibolite phases metamorphism, right? Mainly amphibolite phases. That means the grade of metamorphism is little lower in the Vijayan complex. In the Highland complex and Vani complex, you have granulite phases rocks. So that means high temperature, very high temperature rocks. Whereas in the Vijayan complex, there are little lower grade rocks, amphibolite phases rocks. That means uh, uh, like hornblende, biotite dominant rocks. Okay, no sillimanite bearing rocks in the Vijayan complex. And also you can see the granulite phases metamorphism is also a little bit delayed in the Vijayan complex, although they have it has started almost at the same time, like 550, but it has continued up to 465 million years time. Okay, so this age range is a little bit broader compared to the other two grades. So that means when this Highland and Vani has collided, okay, together, the metamorphism at the I mean, the extreme metamorphism was taken place. That's why the most high temperature rocks are found in Highland and Vani complex. And then these two together collided with Vijayan complex a little later, right? It has become collision. The available collision according to the data uh, seems a little bit delayed, right? So this altogether collided with this one, but it did not create very high temperatures. Relatively less or low temperature conditions were generated. So that's why amphibolite phases metamorphism was there in the Vijayan complex. Okay, right. And there is another important feature you can find in these two complexes, Highland and Vani complexes, which we call the in situ charnocitization. Right? You know the rock charnocite. It's a massive rock and occurring extensively in Sri Lankan lithotectonic units. And you can see in some Highland quarries, in Highland complex quarries, you will see uh, uh, some patches like charnokites, right? But the host rock is almost granitoid, metagranitic or amphibolite bearing, a little bit lower grade rock, but uh, there you have some zones of charnocitization. Okay, so this is called in situ charnocitization, arrested charnocitization. In other words, arrested charnocitization. But this is very typical in the Vani complex. Okay, in Highland complex also there, but it's not very prominent. But in the Vani complex, it's very prominent. If you go to Kurunegala region, you can see this arrested charnocite quarries extensively in areas like Varaddana, Pallandenia, like areas. There are so many quarries which has this characteristic feature. There you can see very big patches, right? Very large zones of charnocitization in the amphibolite phases host rock. Okay, so the name Pallandenia has also come from this phenomena, right? It looks like patches for the appearance, right? Therefore, people have called it Pallandenia, right? The patches bearing area, something like that. Okay, so it's common in Vani complex. We call it arrested charnocitization or in situ charnocitization. So it has happened almost at the same time with the metamorphism, but in the Vani complex, it's a little bit delayed in 535 to 545 or 550 time, right? It's a narrow time interval. That is the date, age coming from this in situ charnokitic patches when the zircon is analyzed. And in the Vijayan complex, you don't see this feature. In Vijayan, you don't see this feature, right? And then uh, is it still time? Yeah, we have 15 minutes, right? Okay, right. So in Vijayan complex, you don't see the in situ chanakitization. And then we observe in our rocks post-tectonic granites. Post-tectonic granites means the granites which have intruded after the metamorphism. Okay, because the metamorphism is the end process of this geodynamic process in our terrain, right? In any terrain, after metamorphism, there will be some stable time, right? There won't be very big collisions or folding or anything happening. So therefore, we call it post-tectonic times. Post-tectonic. During the metamorphism, we call syntectonic time. And if you want to refer something before, like ages like this ages, this time, you can call it pre-tectonic. Okay. So post-tectonic means there is nothing significant in geodynamic processes, but uh, from here and there are some granites intruded into the existing metamorphosed rock, because by that time all the rocks have been metamorphosed. So they still remain as granites because they are not further no further metamorphism, and we can see them still as granites, and that's why we don't call them granitoid, right? If it is granitoid like here, it should be metamorphosed, right? So very faint metamorphism might be there if they just intruded at the last stages of metamorphism, like this age. Okay, but mostly they show unmetamorphosed structures and undeformed structures. Therefore they are called post-tectonic granites. The best example is the granite which is available in Thornigala granite, right? And also Arangala granite in the southern Sri Lanka, also similar type of post-tectonic granite. And uh, their ages, some of their ages have been given like almost the metamorphic time, but I'm not sure about this 580. I don't agree with that age. But it's like almost 550. That means at the last stage of metamorphism, these granites have intruded into the basement. Okay, so this type of granites are characterized by the Thornigala granite and Arangala granite, like the granitic bodies which we have. Okay, and then what has derived from our rocks is the cooling ages, right? So after metamorphism, the temperature conditions getting little by little lowered due to cooling, right? So metamorphism is the peak time of highest temperature, right? It has reached up to 800 900 degrees Celsius, but later on gradually the rocks are subjected to cooling because they tend to uplift from the interior, because metamorphism is taking place within the crust, some 50 kilometers deep in the crust, right? So with the erosion taking place on the top, so we have the erosion taking place on the top, so interior rocks will be coming up little by little gradually, because these materials are taken away by erosion, uh, and you are able to expose these interior rocks little by little later. So during this process, when the rocks are coming up gradually uh, upward, they are reaching lower temperature areas within the crust, shallow areas. So therefore cooling will be dominant structure. Sometimes some reactions can take place during cooling also. So the cooling ages shows some textures, some cooling textures with respect to garnet-like minerals, where the zircon is available in garnet also. You can take them to date these cooling ages, right? So it has given like 400 to even 600. Sometimes at the early stages, they have started to uplift also, right? At the initiation of the metamorphism, there has been upliftment also, right? So from 450 to 600, around 600, there we have cooling ages for the highland complex, and for the Vani complex, we have these cooling ages. Okay, still around up to 400 million years time, there has been cooling taking place within the Sri Lankan crust. So with the available UPB zircon ages, right, and also some monazite ages are also available, plus some very rare rutile ages also there, and they are comparable with the late Proterozoic high-grade metamorphic event in the Sri Lankan basement. It's almost like 550. You can take 550 as our peak metamorphic time. Okay, 550 as the metamorphic age. And you saw the zircons from high-grade orthonisis means the rocks derived from magmatic rocks, igneous rocks, and they show uh, this age, as I said, 1100 million years from Vani and Vijayan complexes. Okay, so for the Highland complex, as I showed before, they show very old ages of detrital grains, and later on some intrusion ages with respect to some granitic rocks at this age. For the Vani and Vijayan also, you have similar type of processes taking place, but at different time intervals. So these ages are very compatible with high-grade terrains in southern India. In India also, in southern part of India, not the northern part of India, uh, below Bangalore, southern India, very similar to our situation. Ages also similar, rocks also similar. That means we were part of this Madagascar, Tanzania, and Antarctica Gondwana fragments, right? We were part of all these Gondwana fragments, right? We were not directly attached to India even any time, but everything was attached to Antarctica, right? India, Sri Lanka, Madagascar were part of Antarctica actually, right? So remember that. So there has been so many models which shows the East Gondwana terrain, East Gondwana terrain. Okay. So it belongs to so-called Pan-African orogeny, Pan-African orogeny, right? So remember this term, Pan-African orogeny. That means the collision zones within the Gondwana terrain, right? This Pan-African orogeny means mountain building process that is common to India, Madagascar, Tanzania, Antarctica. What else? Mozambique, like these countries, right? Part of Australia also, Western Australia. So these are the plotting of the ages from the Sri Lankan terrain. So you can see different rock types, right? Orthonises, metapelites. Pelites means sedimentary rocks, meta-sedimentary rocks, right? And basite, meta-basite means mafic rocks, metamorphosed mafic rocks, mafic rocks. Orthonises direct rocks from magmatic crystallizations. Shrimp means another iron microscope, what is it? Mass spectrometer, another type of mass spectrometer, more advanced one compared to normal SIMS, right? That has also been used. In other cases, all the ages are derived from SIMS or laser ICP-MS, laser LA analysis. So you can see some some important papers. Kroner et al. 1987 and Hosel et al. 1991, Bauer et al. 1991. These are the people who did the pioneering geochronology work for the Sri Lankan rocks. They are all from Germany in 1991 mainly. Okay, 87 to 91 duration. So this is how the ages are coming from our units. You can see very old ages are there. And for the Vani Vijayan, you have this 1000 MA like ages or 1100 MA like ages. Although some old ages are there for the Vani complex also. For example, this is coming from Highland complex, right? Yeah, it's coming from Highland complex. But there are several, few ages, old ages from Vani complex also, right here. 2000 MA like. But for the Vijayan complex, you don't see that old rocks. Okay, with these ages, similar interpretations have been made with rubidium strontium data also, but rubidium strontium ages were given a little bit old time, not very recently. Okay, so like 1970s or so, these ages were determined, but later on there has been no rubidium strontium systematics applied to Sri Lankan rocks because there is a large error associated with rubidium strontium isotopic systematics. So people don't want to apply that systematics in the recent past. So we take the metamorphic age as this one, 550 to 610 in Sri Lanka, but the grade of metamorphism differs, right? That is important because Vijayan complex has lower grade, Highland complex has the highest grade, and Vani complex has uh, granulite, upper amphibolite to granulite, but still higher than the Vijayan complex. Okay, right. So this is what I planned for today. Do you have any questions regarding this content? Do you have any questions? Okay, so at the end of the lecture series, I will give you some references for you to read. That is very important, and most probably I will be finishing this lecture series by one more lecture hour. I can finish my content, but tomorrow I am not going to take the lecture. Okay, tomorrow I think Professor Balasuri, I don't know whether he has finished it or not. He might take, or somebody else will take, right? The lecture will be there, but not mine. Okay, right. So we'll stop here for today.